Alright, in this video we're going to be trying to graph by hand the following function by using a little bit of calculus. This is f of x is equal to 2 times the sine of x plus the sine of 2x. We're going to see if we can go in the same order as what we did in our previous videos. So we're going to start off with the domain of this function. For the domain of this function, we're dealing with simply sine functions, domain of which tends to be all real numbers, unless we wind up with some sort of division in there. I don't think we need to worry about that in this one. After we take a look at the domain, second step is going to be to take a look at intercepts. And we'll start with the y-intercept. For the y-intercept, we'll be plugging in x equals 0, and we'll see what we get. So plugging in x equals 0, this will be 2 times the sine of 0, plus the sine of 2 times 0. Thankfully, I have a calculator here for 2 times 0, and it told me it was 0. Sine of 0 is also equal to 0, so I know that this thing is going to pass through the origin. Oh, no, not 3 yet. We need x-intercepts. For x-intercepts, we're going to be setting our function equal to 0. Oops, sine 2x. And we will be solving for x. Now, first off, this is a lot easier to deal with when we're dealing with the same angle on all of our trig functions, so I'm going to apply a double angle identity to the sine of 2x. Written in this form, it becomes a little bit nicer to try to solve. We have a common factor of 2 times the sine of x that we can pull out, leaving us with 1 plus the cosine of x. Because it's now factored, we are allowed to set either one of these two factors equal to 0. So this tells me that either the sine of x is equal to 0, or the cosine of x is equal to -1. Now the most general solution for this one, this occurs at x equals 0, pi, 2 pi, 3 pi, 4 pi, etc. Or more generally, we can refer to that as k pi, where k is any integer value. For the cosine of x being equal to -1, this will only occur at pi, 3 pi, 5 pi, 7 pi, etc. Or more simply, this will be at pi plus 2k pi, where again, k represents any integer. Thankfully, all of these values are all accounted for in these values, so we don't need to worry about this. So x-intercepts will be at 0, 0, pi 0, 2 pi 0, 3 pi 0, etc. Lots of x-intercepts on this one. All right. After this, we can look into symmetry as well. Evaluate f of -x and see what we wind up getting. Now, fun fact for you, the sine function is an odd function, which means that if I add together multiple sine functions, all of their angles can be factored out to become -2 sine of x minus the sine of 2x. This, of course, would be the opposite of the original function. This lets me know that the function is going to have origin symmetry. In addition to the origin symmetry, I would also like to test this thing for periodicity. Periodicity only applies to trig functions, and that happens to be what we have. Now, normally, when we see a 2x, that has an impact on what the period would be, but because we have a sine of x as well, we're going to go back to simply the period is going to be equal to, we'll use t because it's time, sure. And that'll be 2 pi. So what this means for us is we can figure out what the graph looks like. Graph on the interval from 0 to 2 pi. And then copy this graph and paste and paste and paste and paste and paste, because it'll be the same graph over and over and over. Next up, we'll consider some asymptotes. Asymptotes do not apply here because sine functions do not have asymptotes. So sines do not have asymptotes. So once again, rational functions, other trig functions like tangent, cotangent, secant, or cosecant, exponential functions, things like that will have asymptotes. Sine functions do not have asymptotes. So next up, now that we've done all of these things, let's go ahead and flip over to the other side of the page in case we need to reference back to the other side. Now we're going to figure out our critical points as well as intervals of increase and decrease. So recopying the original function, this will be 2 times the sine of x plus the sine of 2x. Taking a derivative will give us f prime of x. This will be equal to the derivative of the sine function is, of course, the cosine function. And for the second one, we'll be making use of the chain rule on this. So that'll be cosine of 2x times an extra 2 from the chain rule. This is all equal to 0. Now, in order to solve this equation, to get our critical numbers, we're going to have to do something with that cosine of 2x. And for that, just like we did for the intercepts, I'm going to be making use of a double angle identity. Now, cosine of 2x has 3 different double angle identities. The one that I'd like to use is going to be 2 times the cosine squared of x minus 1. The reason I'm using this one in particular is because we already have a cosine of x in here. I want to make sure that the only trig function that I have in here is the cosine of x. Distributing the 2, actually, you know what? Factoring out a 2 would probably make more sense. So this would become simply 2 cosine squared x. The positive 2 cosine of x would become positive 1 cosine of x. And the minus 2 that we would have gotten would become minus 1. Now, this does factor pretty nicely. And the 2 factors that we're going to get out of this, we'll have a 2 cosine of x and a cosine of x for the first term. We'll need a 1 and a 1 for the last term. And in order to get a positive here, we will need a plus here and a minus here. Setting the individual factors equal to 0 and solving for the cosine of x, this tells me that we will have a critical number anytime cosine of x is 1/2, or anytime the cosine of x is equal to -1. Now, because of the periodicity, the only critical numbers that I'm looking for are going to be on the interval from 0 to 2 pi. Then we'll be able to repeat this pattern, whatever we happen to get. So cosine of x is equal to positive 1/2 once in quadrant 1 on the unit circle, and once in quadrant 4 on the unit circle. That'll be at pi over 3 and 5 pi over 3. This one happens to occur at x equals pi. We had already referenced that one. To turn these critical values into critical points, we plug them back into the original function. So let's evaluate f of pi over 3. F of pi over 3, if we plug this back into the original function up here, this will be 2 times the sine of pi over 3 plus the sine of 2 pi over 3. Now, thankfully, pi over 3 and the sine of, pi over 3 and the 2 pi over 3 both have the same sign, and it happens to be equal to the square root of 3 over 2. So given that I have 2 of these and 1 of these, I'm going to add them together to get 3 square roots of 3 over 2. Now, we've already calculated f of pi because we discovered that pi was one of our x-intercepts. So you can reference back to earlier in the video if you care to. Then for 5 pi over 3, this will be 2 times the sine of pi over 3. 5 pi over 3. Plus the sine of 2 times that. That'll be 10 pi over 3. So 5 pi over 3 and 10 pi over 3 also have the same sign, and that is negative root 3 over 2. So similar to the calculation that we did at pi over 3, this will be negative 3 root 3 over 2. So those 3 will be the y values for our critical points. Additionally, we also need to test the intervals. So the intervals that we'll be using for testing will be 0 to pi over 3, pi over 3 to pi, pi to 5 pi over 3, and finally 5 pi over 3 to 2 pi. Again, we only need to figure out what this thing looks like on the interval from 0 to 2 pi, so we should be okay after that. So for my test numbers, I need to pick something less than pi over 3. I'm going to go with pi over 4. On pi over 3 to pi, I'm going to go with pi over 2. On pi to 5 pi over 3, let's go with 3 pi over 2. And for my last interval, we'll go with 7 pi over 4. Little knowledge of the unit circle will treat us well. Now, I want to figure out intervals of increase and decrease, so I'm going to be plugging these into the first derivative, f prime of, we'll start with pi over 4. So I'll be plugging it into, let's use this form of the first derivative. Sorry, casting a shadow on it. We'll use this form of the first derivative. So 2 times the cosine of the given angle plus 2 times the cosine of double that angle. Double the pi over 4 and we get pi over 2. So what we're getting out of this, cosine of pi over 4 is root 2 over 2. And the cosine of pi over 2 is 0. Final answer here is going to be square root of 2. The only thing that I really care about is the fact that it is positive, letting us know that the first interval that we just tested is an interval of increase. For pi over 3 to pi, we're going to be testing pi over 2, once again plugging it into the first derivative. So 2 times the cosine of the given angle plus 2 times the cosine of double the angle. If we double the pi over 2, that'll get us to pi. This will be equal to 2 times cosine of pi over 2 is 0, and the cosine of pi is -1. Final answer for this will be -2. The only thing I care about is the fact that it is negative. The fact that it's negative indicates to me that this is an interval of decrease. Let's keep it going. Doing great so far. F prime of 3 pi over 2. Got that for the third interval. That'll be 2 times the cosine of 3 pi over 2 plus 2 times the cosine of double that angle. That'll be 3 pi. So cosine of 3 pi over 2, that'll be equal to 0, and the cosine of 3 pi is equal to -1. So by some amazing coincidence, we get the exact same expression that we just got for our last interval. This will be another interval of decrease. Interesting. And for our last one, f prime of 7 pi over 4. Am I still in frame? Oh, sweet, I am. This is great. That'll be 2 times the cosine of 7 pi over 4 plus 2 times the cosine of double that angle. We will get 7 pi over 2. Cosine of 7 pi over 4 is equal to root 2 over 2, good old quadrant 4 on our unit circle. And then the cosine of 7 pi over 2 would be the same as the cosine of 3 pi over 2, as they are coterminal angles. So we actually wind up getting the exact same expression that we got for our first test interval. I wonder if that is a coincidence. Just kidding, I don't wonder, I know. So in order, our 4 intervals will be an interval of increase, then decrease, then decrease, then increase, with critical numbers in between. This also now allows us to classify our critical points as being local maxima or local minima. So, first critical point that we have in this interval is pi over 3, comma, 3 root 3 over 2. At that point, we are changing from, sorry, this is number 6 now. At that point, we change from increasing to decreasing, letting me know that this point is going to be a local maximum. Change from increasing to decreasing, you got yourself a maximum. At pi, comma, 0, we're decreasing, flattens out, and then it begins decreasing once again. That is neither a local maximum nor a local minimum. Local maximum and local minimum is where it changes between increasing and decreasing. And our last critical point was at 5 pi over 3, comma, negative 3 square root of 3 over 2. At that point, we are changing from decreasing to increasing, which means that we are dealing with a local minimum. Anytime we change from decreasing to increasing, that is a local minimum. So we have now officially classified all of our critical points. Feels good, feels real good. So, moving on to another page, just because, oh wait, I have 2 6s here. Oh, shoot, that was 6. This must be 7. Guys, I did 6 plus 1 wrong. All this calculus is fine, but man, arithmetic is just beyond me. Alright, that one was 7, so this one will be 8. Intervals of concavity and inflection points. I'm going to recopy from the previous page f prime of x. That was equal to 2 times the cosine of x plus 2 times the cosine of 2x. We're going to differentiate this one more time so that we can figure out some intervals of concavity, and we'll see what we can get done. So, differentiating this will look very similar to the previous one. Derivative of the cosine function is the negative sine function. So we'll see negative 2 times the sine of x. Then we'll see minus 2 times the cosine, 2 times the sine of 2x. And then the chain rule says pop on an additional derivative of the inside. That'll give us an extra 2. So we are looking at negative 2 times the sine of x minus 4 times the sine of 2x. With that in mind, we're going to be setting this equal to 0 and trying to solve for the appropriate values. Now we can use that double angle identity that we used for the intercepts once again and say that the sine of 2x is the same as 2 times the sine of x times the cosine of x. Now I see once again we do have a common factor of the sine of x here. Excuse me, we'll go with negative 2 sine of x as our greatest common factor. So first term would become 1. Second term, if we take away the 2 times sine of x, we'll have plus 4 times the cosine of x. That'll be equal to 0. Now one of these is going to be a little bit easier to solve than the other one, so we'll just sort of give a visual representation of the other one. So negative 2 sine x, if we set this equal to 0, we're going to get that the sine of x is equal to 0. Whereas this one gives us that the cosine of x is equal to negative 1/4. This I can solve no problem. This will be at any multiple of pi. We'll call it x equals k pi. This one is not. So I'm going to describe these angles according to unit circle trigonometry. Now, cosine on the unit circle is the x-coordinate, so we want the two angles where the x-coordinate is negative 1/4. So the two angles in question would be this guy right here, and then we'd have one down here in quadrant 3 as well. So for now, I'm just going to refer to these guys as theta 1 and theta 2, because I really don't feel like calculating the arc cosine of negative 1/4, and quite frankly, I don't think that we need to at this moment in time. So with that in mind, our test intervals are now going to go from 0 to that first theta 1, from theta 1 up to pi, from pi to theta 2, and then from theta 2 all the way up to 2 pi. We're going to test these for intervals of concavity, and then we'll figure out some inflection points. Based off of the graph that I've made here, I believe that we will be safe using test points of x equals, for the first one, pi over 2. For the second one, negative 1/4 isn't as big as negative 2 root 2, so we'll go with 3 pi over 4. Followed by 5 pi over 4 for the same reason. And finally 3 pi over 2 for the last interval. We'll figure out the concavity at these points. So we will be plugging these into this form of the second derivative that we just found, which is negative 2 times the sine of x minus 4 times the sine of 2x. And hopefully all will be well. So f double prime of pi over 2 is going to be equal to negative 2 times the sine of pi over 2 minus 4 times the sine of double that angle. That is going to be negative 2 times 1 minus 4 times 0. I don't care that that's equal to negative 2. I care that it is negative. So on our first interval, we can count on this thing being concave down. We'll use CD for concave down. For 3 pi over 4, that'll be negative 2 times the sine of 3 pi over 4, 3 pi over 4, minus 4 times the sine of double that angle. That's going to be equal to negative 2 times root 2 over 2, minus 4 times sine of 3 pi over 2 is negative 1. This will become positive 4. That will not be bigger than positive 4, so this is going to wind up being positive. So concave up. Concave up. Continuing on, f double prime of 5 pi over 4. This is probably going to look very similar to the previous one. So negative 2 times the sine of 5 pi over 4 minus 4 times the sine of double that angle, that is 5 pi over 2. This will be negative 2 times negative root 2 over 2 minus 4 times sine of 5 pi over 2, that's coterminal to pi over 2, that is positive 1. This is going to wind up being a negative value, letting us know that on this interval we are concave down. And finally, f double prime of, last test point is 3 pi over 2. That will be negative 2 times the sine of 3 pi over 2 minus 4 times the sine of double that angle, that'll be 3 pi. This is negative 2 times negative 1 minus 4 times 0. That is a positive number. That is 0. We are going to wind up getting a positive, oh, sorry, got ahead of myself. I was going to say greater than 2. It's equal to 2, which is greater than 0. So it'll be concave up on this interval. Oh boy. So with that in mind, I am going to take all of the information from 6, 7, and 8 and see if we can come up with some decent looking intervals of increase and decrease as well as concavity. So with that in mind, here is 0 to 2 pi. Should probably make these a little lower. F prime will go up here. F double prime will go down here. Smack dab in the middle I know is an important point. That'll be pi. For our intervals of increase and decrease, important values that we had were pi over 3, pi, and 5 pi over 3. So what I'm going to do is take this interval, split it into thirds, take this part of the interval and split it into thirds as well. Point out that that'll be 5 pi over 3, and this will be pi over 3. So for our intervals of increase and decrease, we got that this thing was equal to 0 here, 0 here, 0 here. Outside of that, it was increasing on the first interval, decreasing on the next interval, got back to 0, but then started decreasing again. We'll expect to see the graph flattening out at that point, then starts increasing once again. For our intervals of concavity, this one was a little bit more complicated. Pi was an important point. We had a number that was slightly bigger than pi over 2. Pi over 2 would be right here. And our value that we referred to as theta 1 was right about here. Then 3 pi over 2 would have been right here, and slightly smaller than that, we would have gotten our theta 2 value. So at theta 1, concavity was 0. It'd be nice and straight there. Then it was 0 at pi. It was 0 at theta 2. And it was also 0 at our two endpoints of the interval. It started off concave down until we got to theta 1, where it became concave up, until pi, where it became concave down, until theta 2, where it became concave up, until 2 pi, where it presumably would change back. we are going to have some fun with this graph. And that's fun with a capital F and a whole bunch of U's right afterward. So try to make a similar looking interval here. We'll mark off all of the important parts. Here's 2 pi out here. Halfway in between, we'll have pi. Split this into thirds right about here and here. Here's pi over 3. And then do the same over here. Here's 5 pi over 3. So a little bit earlier than 5 pi over 3. Right about there. This was theta 2. And then over on this side, right about there, would have been theta 1. Additionally, from a couple pages ago, we also have the actual local maximum and local minimum. Local maximum was supposed to be at 3 square roots of 3 over 2. Local minimum was supposed to be at the negative same value. So negative 3 square roots of 3 all over 2. X-intercepts occur right here, and here, and here. Local maximum occurs right here. Local minimum occurs right here, 5 pi over 3, negative value. And let's see if we can match everything else up. So from x equals 0 to pi over 3, we are increasing and concave down. Increasing and concave down looks just like this. Then we will be decreasing and concave down until we hit theta 1. Probably should have calculated the corresponding y value, but I didn't, because I am recklessly irresponsible. After we hit theta 1, this thing is going to be decreasing but concave up until we hit pi. So from pi, I'm going to go decreasing and concave up, and then connect the two sides. At pi, it's supposed to flatten out, but then go back to decreasing and concave down until we hit that theta 2. I believe what we're going to see is basically just the mirror image of what we just created, which was, that should come down this way, and then go to, oh crap, oh boy, all right. Little mix up there, that's okay. And then increasing and concave up until the end. So it looks kind of like a trig function, but with a little extra wiggle in the middle. I am very interested to see how I actually did here. So what I'm going to do is head over to the graphing calculator and see if we see the same thing on our graphing calculator as what we just created here. The original function was 2 times the sine of x plus the sine of 2x. And we'll limit ourselves to just 0 to 2 pi with the knowledge that this thing is going to repeat itself over and over. So we'll go from 0 to 2 pi. And then in the y direction, why don't we just say negative 3? All the way up to positive 3 with a scale of 1. Here's the part where you cross your fingers real good and hit graph. All right, feeling good about the start. Didn't really nail that point of inflection. But you know what? Feeling pretty confident after that. Yeah, that's good enough to take to the bank. All right, cool. Wow, trigonometry is a lot of fun. Now, I'll be sure to upload this half-hour long practice video for y'all to take a look at.